Okay, so now we get to talk about the specific heat capacity. All right, so consider once again the idea of measuring the temperature of water, right? So here we have a beaker, with some amount of water, and we have a thermometer measuring its temperature. All right, so now this is the premise. You can determine the relationship of the change in temperature of the water based on the mass of water used by dropping a constant mass of some object. Let's say it could be aluminum, it could be iron, basically a metal piece, the same metal piece, but the thing is this, the metal piece has to be held at a high temperature, let's say 120 degrees Celsius. The specifics don't really matter too much right now, but the idea is that you're going to be changing the amount of water present, and you're going to be measuring the change in temperature of the water as you drop this same piece of metal, which is initially held at some high temperature. But the initial temperature is the same in each trial. So if you actually measure the change in temperature versus the mass of the water, what you find out is that the graph is not a linear graph. You could try to come up with a good fit to this thing. Like I came up with an exponential fit, and it's okay. I mean, the correlation value is 0.992. It's not super great. As you can see, some of the data points are not exactly on part. And the reason is because it turns out to be the case that if you actually plot the change in temperature of the water versus the inverse mass of the water, that actually results in a direct linear correlation. And for this particular data set, I obtain a linear equation y equals 251.2x plus 0.07402 as the linear fit. And the correlation value is really good, it's 0.999. So this is as linear as it's going to get. All right, so this is what this relationship tells us, right? The increase in temperature or the change in temperature of water as a result of the inverse mass of the water. Because of the correlation here, what we do know is that the change in temperature of the water has to be the y of the equation, and the inverse mass of the water has to be the x. Since this is a line, there's going to be a slope associated with it, and notice that the value of the intercept is pretty small, meaning that this is probably within error supposed to be 0, right? So I'm going to exclude the y-intercept for now and only focus on the slope. So we have the change in temperature for y, inverse mass of water on the x, and then we'll have some slope. So what I'm going to do is solve for the slope, okay? And that means that I will multiply both sides by the mass of water. Now we have mass of water multiplied by the change in temperature of the water equaling the slope of the line. Alright, so here's where the information regarding heat and kinetic energy comes into the picture. We know that temperature, after all, is a measure of heat. And based on the description of the units of heat, we know that we have to have, here we go. So heat is a representation of temperature. So the fact that we have changes in temperature here means that we have to be looking at some sort of heat. But what this means is that the slope has to contain heat within it, and some other constant multiplying the heat. Now the reason there has to be another constant and the slope isn't exactly the heat is because if you look at the units, mass is in grams, change in temperature will be in degrees Celsius, and the heat itself is going to be in units of joules. So grams and degrees Celsius do not equate to joules. So that tells us that this extra constant here that arrives from the slope is going to have to make the units work out. And specifically, if you solve for the C over here, so cross multiply by C and divide by gram degrees Celsius, you'll find out that the units of C will be joules divided by grams degrees Celsius. And in essence, this particular constant is what we call the specific heat capacity of the substance. In the case of this plot right here, we'll be talking about the heat capacity of water itself. And in equation format, if we want to be technical, we will multiply by C and we will get the traditional, you probably remember this from earlier chemistry classes, Q equals mcat. For this particular equation, we're talking about the heat of water equating to the mass of the water multiplied by by its specific heat capacity and its change in temperature. So that's the famous equation, and this is a typical experiment that you could perform to find out the heat capacities of your substances. So it's kind of a cool setup. All right, now the other thing that I need to tell you in regards to the specific heat capacity is that each substance has its own value of specific heat capacity. They're all in joules per gram degree Celsius, um, but they all differ in their values. Now, one thing that I want to point out to you is that generally speaking, if you look carefully, so here I highlighted of certain molecules in blue, like NH3, ethanol, octane, helium, dihydrogen, methanol, dinitrogen, neon, um, and even sodium. All right, so generally speaking, what you can see for these substances that I highlighted in blue, the values of the heat capacity are all greater than 1. And generally speaking, notice that there are some exceptions, but generally speaking, as the value of the heat capacity increases, we tend to associate that increased value of heat capacity with nonmetals. And the reason why is because the nonmetals have electrons that are part of covalent bonds, and as a result, the electrons are localized within the molecule. And it's this localization of electrons that prevents the amount of temperature to rise up. Free electrons floating around, on the other hand, create plenty of kinetic energy that raise the amount of temperature. But in non-metallic substances, covalent substances, you tend to have electrons localized, and the change in temperature tends to be rather small. And this is, in essence, the key idea behind identifying insulators, things that will prevent changes in temperature from happening. Um, on the other hand, the vast majority of the metals found on this list have values that are generally less than 1 for the heat capacity. And generally speaking, as I said, this will belong to metals. And the reason why is because metals have electrons that are actually fully delocalized within the surface of the metal. And these electrons are free to flow. You could even think of them as a sea of electrons sitting on top of the atoms themselves, the nuclei of the atoms. And these electrons are free to flow, so it's easy for them to change their temperature of the material as a result of how easily they can change the kinetic energy of electron movement throughout the material. All right, so generally speaking, that's what's happening, and there's some discrepancies on the table, mind you, but in general terms, covalent molecules with localized electrons have higher specific heat capacity, and the final temperature is lower than those with smaller heat capacity values. All right, so I'm going to stop the video right here, but in the next video, I'm going to show you a few examples where we actually do calculations with the specific heat capacity. So tune into the next video.